Hi everyone and welcome back to Physics 2A. Today I wanted to go in depth into vectors. So I'm going to start by reminding you guys what vectors are. So vectors have a magnitude and a direction, okay, and they're usually represented by an arrow. So I wanted to show you guys a few examples of vectors, starting with velocity. So here we have a little car and we have an arrow telling you which direction this car is moving, and that would be our velocity vector, okay? We can also look at acceleration with vectors, and it tells us, for example, in a car, if you're speeding up or slowing down, and that would give you a positive sign in front of the acceleration vector or a negative sign in front of the acceleration vector, okay? Now, if we're thinking about acceleration, I put a question here. How can we change the acceleration of a car? Okay, so think of different ways that we can either speed up or slow down. One way to speed up, of course, would be the gas pedal, right? Step on the gas. You'll be accelerating, okay? That's typically how we think of it, is acceleration is positive. But acceleration can also be negative, okay? And we can slow our car down, which is accelerating in a negative direction, by putting on the brake, okay? So whenever you think of acceleration, it can be positive and negative. So keep that in mind. Also, displacement can be a vector. So think of it this way. I'm going to draw down here. If I'm just looking at an x-axis here, okay, and I start here, okay, at this position, and say I get to here, I moved, okay, let's see, 1, 2, 3, 4 spaces, okay, and that was to the right. So this is also a vector, displacement vector, okay, and we put it, represent it by x bar, okay, that's what these bars are on the top. That tells you that it's a vector, and this moved in the positive direction, okay. Now on the other hand, if I started here, again, I started at this spot, and I moved a couple this way, okay, so this is my vector now. I had an x displacement in the negative direction, okay? So keep these in mind. We will be using them quite a bit to represent acceleration, velocity, displacement, and even forces, okay? And that's gonna tell you which direction the force is being applied and so on. Okay, so moving on, talking about vectors, we want to know how to look at them graphically and algebraically, okay, and we want to know how to add them together, because if we have a car going down a road and say they're going 5 miles in one direction, and then they turn and do a different direction, those are two different vectors being added together. Okay, so a car moving this way, and then it decides to turn and it goes that way. Okay, so I want to show you this method. It's called tip to tail. Okay, and let's pretend that we have two different vectors, A and B. Okay, so let's say our A vector goes in this direction, and we have our B vector going in this direction. Okay, so slightly slanted. And we're trying to add these together. Okay, now what we'll do is we'll do this tip to tail method. Okay, and once I show you, it'll make sense. So I'm gonna first draw my A. So that's my first vector. Now I'm going to put my second vector, and it's gonna be tip to tail. So I'm going to get the tip here and then add my B vector here. Okay, and so this is my new or I will create my new vector based on these two. So now I will go from this tail to this tip and connect them. Whoop. That was kind of a poor job there. But you get the gist. I get from this tip, this tail to this tip, make a line, straight line, and that will be my resultant vector. Okay, so now that's my R. Okay, so this is how you add vectors graphically. Okay. I wanted to show you this in a little bit of a better structure here. I don't have the greatest drawing skills when it comes to not a pencil and paper. So here again, I have A and B added together to make my resultant vector. And typically, again, we represent vectors with a bar or maybe even an arrow above our letter, whatever the vector letter is that we're representing it with. This is not very common, but this one and this one definitely are. Sometimes they're even just bolded like this. But we will usually be using a bar or an arrow. Okay, so here's another representation. This time we have 3 vectors to add, but it's the exact same thing. It's tip to tail. So here's my A, then I put B down, tip to tail, and then I add C, tip to tail, and then I connect them. Okay, and that would be again my R vector. Okay, so hopefully this is all making sense. If not, maybe go back through. The text doesn't talk a lot about this, but I want you guys to understand this before we get into forces and such, because this will be very helpful. Okay, now I wanted to go over subtracting vectors because it's not really, I guess, intuitive, but once you see it, maybe it will be. So again, let's say we have A, vector A, and we have B. I'm gonna go like that, okay? But now we're subtracting them, okay? Or I like to think of it as adding a negative B. So this can also be represented like this, okay? A minus B, or A plus a negative B. This is how I like to think of it. Because that negative acts on that B, okay? And I'm going to redraw this, but now add them. So this negative acts on that B. What it does, it completely reorients this guy. It basically just flip-flops it. So now instead of it pointing that way, it's going to be pointing in the opposite direction, like so. Okay? So see, it's the exact same direction. I'm sorry, not the exact same direction, the same magnitude, but we are now changing directions. Okay? So again, with that tip to tail method, I have A going this way. And now, instead of in the last slide, now it's going to be pointed down, B. Okay, now notice the difference. So B was going that way, now it's going the complete opposite way. Okay, and then we have our resultant vector, tip to tail, R, there we go. Okay, so this would be graphically. Okay, we are subtracting the vectors. Now, I also wanted to mention multiplying and dividing by a scalar. Okay, so say we have some vector A, like we have here, and we multiply it by 2. Okay, all that does is it takes that vector and makes it twice as long. Okay, so this is some length A. Okay, so what this does is it says, okay, let's take that length and multiply it by 2. Okay, it's going to be the length or the magnitude. Okay, now again, over here, we're doing the exact same thing except for dividing by 2. But it's very similar. It acts very similar. now what we are doing is we're saying, okay, 1/2 times A, or we can also say that length divided by 2. Okay? Same basic thing. Now, I did want to mention on this slide that multiplying 2 vectors together, there is something that we can use to do that. It's called the dot product. But there is no such thing as dividing vectors by vectors. So I can't say A divided by A. That doesn't make any sense. Okay, so don't worry about that. Just to remember multiplying and dividing by a scalar. Okay, remember that's just a magnitude. That's just a number. Okay. All right. So real quick, I want to talk about components of a vector. So we go and we have a vector in said direction. We have a vector A, okay, with a magnitude of A as well. When I say magnitude, again, I just mean the length. So if I have a vector A and I want to know its magnitude, sometimes people will put these little bars on them to say magnitude, or you can just represent it by A, okay? Now, in vectors, we have X and Y components of that vector, okay? And if we want to break that down, we will have A bar equals AX plus AY. Okay, so this is how we break down vectors into their components. Okay, let's see. If we want to solve for these guys, we can use trigonometry like I talked about in the last lecture. We have our trig identities, okay, that we can use. So if I want to solve for AX, okay, say I want to solve for AX first, and I know my magnitude and I know theta. If those two things are known, I can solve for my AX and my AY. So first with my AX, I'm going to say, okay, how am I going to solve this? How am I going to find it? So I know that one of them is going to be my adjacent, and one of them is going to be my hypotenuse. Because remember, the long length of the triangle is our hypotenuse. And remember, we're looking at this right triangle here. Okay, so we have our hypotenuse and we have our adjacent sides. So if I have my adjacent and my hypotenuse, whoops, what is that going to be? Which identity? Cosine. Okay, so we have our cosine theta equals our adjacent over hypotenuse. Remember, ka in SOHCAHTOA. Okay, so I have cosine theta equals our adjacent, AX over A. Okay, and then we can solve for AX using a bit of algebra. So I have AX equals A times cosine theta. Okay, and you could do the exact same thing with AY. Okay, and remember that, or if you look at this, you can see that from here to here is the same length as from here to here. Okay, so we know that this AY is the same as this length, and we can call that AY as well. Okay, so I now know my opposite, which is AY, and my hypotenuse again. So opposite and hypotenuse gives me sine. Okay, so we can solve for AY from there. AY equals A sine theta. And there we have it. Now we have broken down our vector A bar, and we can solve for every side, every component. Okay. All right. I think that's about it for now. I'm going to stop this video and then I will give you guys some examples in the next one. All right, thanks.